So we've been talking about hybridization, taking those atomic orbitals and combining them to form new hybrid orbitals. In the Lewis model, elements in the third row, third period, or larger elements can exhibit expanded octets. And so that's where we got those shapes like the Trigonal Bi-Pyramidal. So in valence bond theory, this corresponds to including some d orbitals in the hybridization. And this can happen because the energies of the 3d orbitals are similar to those of the 3s and the 3p. So here we have 3s, 3p, and 3d orbitals. And we've looked at combining an s and 3 of the p orbitals, and we call that sp3 hybridization. We can also include 1 of the d orbitals. So in the hotel analogy, these 3 sublevels are 3 rooms on the same floor of the hotel, right? And so when you're hybridizing orbitals, it's like remodeling these rooms and reconfiguring them so that now we broke down the wall between the S room and the P room, and we took down the wall between the P and the D room, but we put up another wall here, and so now we have 4 beds in that D room, and the rest of these are all equivalent in energy now. They're all the same cost to stay there in those beds, and so now we have 5 degenerate orbitals. Those 4 d orbitals are still there. They were empty before and they're empty now. So as we learned from Vesper theory, 5 things will arrange themselves in 3-dimensional space as a trigonal pyramid. So when we see molecules such as arsenic pentafluoride, we can look at the Lewis structure. We see that there are 5 single bonds around that central atom of arsenic. Arsenic will do that sp3d1 hybridization and form 5 hybrid orbitals. Each of those is going to be half-filled and can then form a sigma bond with a fluorine atom. You could also include 2 of the d orbitals instead of just 1, and then this is called sp3d2 because it's an s orbital and 3 p orbitals and 2 d orbitals. So now we have 6 degenerate orbitals, and they will arrange themselves like an octet. Not an octet, octahedral, sorry. An octahedral. So sulfur hexafluoride, sulfur forms 6 bonds, 1 each with 6 fluorine atoms. And it can do this. It has 6 valence electrons, but to make 6 bonds, it needs 6 half-filled orbitals. So it can hybridize to form sp3d2 hybrid orbitals. Now it has 6, 1 for each of its valence electrons, and it can form 6 bonds. Any questions? So how do we know which hybridization scheme we should use for a specific molecule? So the real answer to that is that the degree and type of hybridization is calculated so that you get the molecule with the lowest energy. That's beyond the scope of this class. So we're going to go with the second option that I'm calling good enough for Chem 1A. We're going to assign the hybridization scheme from the electron geometry on the interior atom. So we're going to use Lewis theory and Vesper theory to help us predict what the hybridization is. It's not 100% accurate, but it's good enough for Chem 1A. So it's based on the number of electron groups around the central atom. If you have 2 electron groups, that means you need 2 hybrid orbitals. And so you're going to use an sp hybridization. So if I need 2 electron groups, then I use sp hybridization. Okay. If I need 3 electron groups, that makes a trigonal planar electron geometry 1, 2, 3 sp2 hybridization. If I need 4 electron groups, tetrahedral shape, SPPP 1, 2, 3, 4, sp3 hybridization. Okay, does that make sense? For the YouTube people, I wrote SPPP on my fingers, and I'm counting 1, 2, 3, 4. So Trigonal Bi-Pyramidal is 5 electron groups. So SPPPP, I ran out of fingers on my left hand. So then what do? Well, stick up another one, right? We need to pull in a d orbital. And for 6, we need to pull in 2 d orbitals. So the idea here is we look at the Lewis structure. We see how many electron groups are around the central atom. Remember, an electron group is a lone pair, a single bond. A double bond is one group. A triple bond is one group. A single electron, we're not going to run into those, but if you had a free radical, that would also count as a group. So you count the number of electron groups, and that's how many orbitals need to be hybridized. You start with S, you go through the 3 p orbitals, and then into the Ds if you need to. Does that make sense? So here's our set of instructions. First, you start with the Lewis structure for the molecule. Use Vesper theory to predict the electron geometry. That's looking at the number of electron groups. Then you're going to select the correct hybridization scheme based on the number of electron groups. Then we can sketch the molecule, start with the interior atom and its orbitals, and then show how it overlaps with the appropriate orbitals on the terminal atoms. We can label all the bonds using sigma or pi notation, followed by the type of the overlapping orbitals. So we'll do some examples. Write a hybridization and bonding scheme for xenon tetrafluoride. So the first thing we have to do is do the Lewis structure. So we'll put the xenon in the middle and put the fluorines around. Then what's the next thing we have to do when writing a Lewis structure? We need to add the dots. First, we need to figure out how many dots we can add, right? So we have to figure out how many valence electrons are present in this molecule. So the xenon has 8 valence electrons, and there are 4 fluorine atoms, and how many valence electrons do they each have? 7. So let's see, 4 times 7 is 28, plus 8 is 36. Yeah. 36 electrons. So I count the bonds first. I've got 2, 4, 6, 8 electrons in those bonds. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've got 4 more electrons I need to put around. Who can handle more electrons? Xenon. Xenon's down in period 5. It can expand its octet because it has d orbitals available. So I'll put those electrons on the central atom. Xenon has an expanded octet, but it's big enough that it can handle that. Yes?
Okay, so you just said that it has a d orbital spare.
Right.
Let's say that neon is in the middle. What would happen then? Could we not add dots around it?
If neon was in the middle, you could not expand the octet.
So then is that when you have to wrap it?
Well, then it can't form more than 4 bonds. It just doesn't happen.
Okay.
Yeah. So we won't ever have to do that because it doesn't exist. So in the hotel analogy, on the 2nd floor there are only 2 rooms, the S room and the P room. There is no D room. And so if we try to put more than 8 people on that floor, it doesn't work because you can't expand. That's the end of the hallway. There's nothing there. You go up to the 3rd floor, and the S, P, and D rooms are there. The S and the P rooms are cheaper, and then there's the D room, but people don't usually use that one because they go up into the 4S room because it's less expensive than the D room. But the D room is there. So you have things like phosphorus. Phosphorus has no electrons in the D orbitals, but the D orbitals are there. Because in a hotel, if there's no one staying in the room, does the room disappear? No, it's just empty. These orbitals are all there, it's just that most of them are empty. Does that make sense?
So like neon tetrafluoride is not good.
Neon tetrafluoride could have, well, no, it couldn't because there's too many electrons. Yeah.
So it just wouldn't be a thing.
It just wouldn't be a thing. Yeah. And, you know, neon really doesn't form compounds at all. And that's really why. Yeah. Okay, so there's our Lewis structure. So now we identify how many electron groups on the central atom? Not 2. There's 2 lone pairs. There's 6 electron groups, right? The 4 single bonds and the 2 lone pairs. So we have 6 electron groups. So that means we need 6 orbitals to hybridize. So we start with S, and then we go into the P room. We got 3 beds in there. We're looking for 6 beds in the hotel. And where do we go next? Into the D room. And how many D beds do we need? 2. So we've got an S and 3 P's and 2 D's. That gives us 6 orbitals. And we'll hybridize those together. We'll remodel the hotel so that we have one room with 6 beds in it. So that's the hybridization. So if we are to draw this, a bonding scheme, and identify what these different things are, well, I guess we should look at the orbital diagram first. So we're going to end up for the xenon and this is something we're going to need to do in the worksheet for today. So these 6 are called sp3 d2, and then there's also some d orbitals that are left just empty. They were sitting there empty before, and they're still going to be empty. So then we look at, well, xenon has how many valence electrons? 8. So let's put those 8 electrons into these hybrid orbitals. So 1, 2, 3, 4, 5, 6, 7, 8. They have to pair up. We're going to fill up those hybrid orbitals before we would go up into the d orbitals. And then let's look at xenon. No, that is xenon. We just looked at xenon. What am I saying? Let's look at fluorine. Now, we are staying with a more simple idea that the terminal atoms, like the fluorine here, do not hybridize. It's not exactly true, but it's close enough. So fluorine is going to have, it's just regular atomic orbitals. So it's got S and P, and we know that it has 7 valence electrons. And so they're going to fill in, they're going to be in the S orbital, and then they'll start filling up the P orbitals. And we'll end up with an orbital diagram that looks like that. So the question is, what about the S here? Well, I can draw those in. So let's do that on just one of these. So here's the S orbital for fluorine, and that's got 2 electrons in it. And then there's 2 other p orbitals. So there's one going up and down, and that's got a pair of electrons. And then there's one going in and out the other way, and that's got a pair of electrons. And you can see why I didn't draw all of those for all of them. We can't even see what it is.
So for the picking up there, why didn't you include the S as well?
So I didn't include these in the bonding description because these are not involved in bonds. These are lone pairs. Yeah, good question. So we're only doing these descriptions for the bonds, but each bond will have a description. Any other questions? I really like valence bond theory because once you get your mind around it, we can visualize this thing. We can visualize putting these in overlapping, and it's like they're holding hands or something. And you can kind of see it in your mind. You can at least, we can actually draw pictures. They're hard to draw, but we can draw pictures of them. So let's do another one. HCN. So first thing, we have to start with the Lewis diagram. Now this is suggestive of how we should draw the structure, putting carbon in the center. So I'm going to put H, and then C, and then N. And then we have to count the valence electrons. So a hydrogen has 1, and carbon has 4, and nitrogen has 5. So we've got 10 electrons that we can put here. We've got 2, 4, 6, 8, 10. We run out of electrons very, very quickly. So we need to share. So I'll take a lone pair from the nitrogen and share it with the carbon. And we're still not having enough. So I'll take this lone pair from the carbon and share that with the nitrogen. And now we've got octets. And if you check the formal charges, those are going to be 0. So this is our Lewis structure. To do the bonding with valence bond theory, we need to identify how many electron groups are in the central atom. 2 electron groups. Okay? So we have 2 electron groups. So then what's the hybridization scheme?
Oh.
SP. I need 2, right? S and P. So this will be SP hybridization. I know that because I look at the Lewis structure. The Lewis structure says I need 2 electron groups, so I'm going to need SP hybridization. Okay, so let's look at the orbital diagram for carbon. So I'm going to do the original atom as well as the hybrid. So the original atom, there's p orbitals and s orbitals, and carbon has 4 valence electrons, and so there will be 2 in the s and 2 in the p. When it hybridizes, we know from the number of electron groups that we need an sp hybridization. So we're taking one of the p orbitals and that s orbital, and we're going to hybridize those together. There are still 2 p orbitals that remain unhybridized. So those are p, and this is sp. Because I took an s orbital and a p orbital and I hybridized them together. In the hotel, what I did is I broke down the wall between the s and the p room so that one bed is included in the same room as the s, and then I put up another wall and these 2 guys are in their separate room. I could draw pictures of that if you want me to, but so now I need to put electrons into these new orbitals. And you might think, well, we got 1, 2, 3, 4, right? Because that's what we're supposed to do. We're supposed to fill up the degenerate orbitals before we move on to the next. But that's not going to work, is it? We really should have 4 half-filled orbitals here. We definitely need 2 half-filled orbitals to make those bonds. So how can we understand why this is not the case? The p orbitals here are only very slightly higher in energy than this new sp hybrid. And so for these electrons to move into here, it's only a small increase in energy. But they get a pretty big benefit because instead of having to share an orbital, they can have their own orbital. So you think about the electrons going into the hotel, and it's like, okay, for 50 cents more per night, you could have your own bed. You're like, heck yeah, I don't want to sleep with a stranger. So instead of going in there, these 2 electrons will be up here. That gives us 4 half-filled orbitals. These can make bonds, and these can make bonds. And if we look at this carbon, how many bonds are there? There's 2 electron groups, but there's 4 bonds, right? So any questions? I know this is a little confusing. Why did I do that? Yes?
So, the SP to the right, you could fit 4, but you can add extra E and you could
Yeah, so we could put 4 electrons in the sp hybrid orbitals and leave this empty, but we don't want to do that. That's not correct, because then there would be no half-filled orbitals to make bonds, right? These p orbitals are there. They were empty before, but they were there. And so instead of having these pair up, I'm going to put those electrons up here. And so sometimes it's kind of hard to know, well, should I pair them up in the hybrid orbitals or should I stick them up into the unhybridized orbitals? And the Lewis structure gives you clues about that. So I look at the carbon and I see that it has 4 lines coming from it, 4 bonds. That means that in my hybrid orbital scheme, I should have 4 half-filled orbitals, okay? And then looking ahead even further, this triple bonds are made using 1 sigma bond and 2 pi bonds. Pi bonds happen between p orbitals. So because I'm going to need 2 pi bonds there, that's where these 2 p orbitals are going to come in. Does that help? And then let's draw the nitrogen over here. So the nitrogen we're going to assume is unhybridized. So it's got p orbitals and the s orbital, and we put the electrons in. It's got 5 valence electrons. So we put 1, 2, 3, 4, 5. Oh, and then we also have hydrogen, so let's not forget hydrogen. Whoops, I don't want to make it red though. I'll make it orange. There's hydrogen. Easy to overlook because he's just sitting there with 1 electron. So this is carbon's unhybridized orbitals. We're going to be looking at the hybrid orbitals. So I'm just going to say, okay, well, we needed to think about that, but that's not what we're using. So all of our bonds here are going to come from half-filled orbitals overlapping. So carbon is going to overlap one of its sp orbitals with nitrogen and 1 with hydrogen. And that's how it gets hydrogen on one side and nitrogen on the other side. These 2 p orbitals for carbon are going to be used to make pi bonds. And those will make pi bonds with the other 2 p orbitals on the nitrogen. So let's see if I can attempt to draw this. Okay, so here's carbon in the middle. I'm going to go with the book's convention of using blue for p orbitals, red for s orbitals, and purple for hybrid orbitals. So carbon has 2 hybrid orbitals. It's got an sp and another sp, one on each side, because that's what 2 groups do. They make a linear. So I've got these sp hybrid orbitals, and those each have 1 electron. Did the book use blue for p orbitals or red? I can't remember. I think it used red for p orbitals. Pretty sure. I'll go with that, even though I'd rather not, but I'll use red. The carbon then also has 2 unhybridized p orbitals. So those are going to be perpendicular to the hybrid orbitals. And so we're going to have 1, well, that's lopsided. 1 up here. Now a p orbital has 2 equal-sized lobes. These sp hybrid orbitals have a small lobe on the other side, but it's not very significant, and it makes the drawings really complicated, and that's why we leave it out. So this is 1 orbital, that's 1 orbital. This thing right here, even though it has 2 lobes, is 1 orbital. So that p orbital has an electron in it. And then there's another one kind of going in and out of the page, the screen. And that also has 1. So these are the p orbitals, and then I have 2 hybrid orbitals. You with me? So then if we have the hydrogen, hydrogen is over here. Hydrogen has a 1s orbital that's got 1 electron in it. And so that's going to overlap with the sp hybrid orbital on the carbon. And while we're over here, let's just go ahead and name that bond. The s orbital really can't, it's not really an end-to-end because it doesn't have an end, right? But it's definitely not a pi bond. Then this is overlapping the end of the hybrid. So this is a sigma bond. And it's between carbon and hydrogen, right? So the carbon, what kind of an orbital is carbon using? The sp hybrid orbital. And then the other element is hydrogen, and it's using an s orbital. So I've got carbon with its sp hybrid orbital and hydrogen with its s orbital, and that's what's overlapping and forming this sigma bond. So I've accounted for this one and this one. Okay? Let's do the other hybridized orbital, this sp. That's going to overlap with one of the p orbitals on the nitrogen. So over here, we've got the nitrogen, and it's got 3 half-filled p orbitals. So there's one that goes like this, and there's one that goes up and down, and there's one that goes in and out of the screen. Each of those has 1 electron in it. So I made a sigma bond here. So let's describe that one before we go on. This bond is a sigma bond, overlap end to end. It's between carbon and nitrogen. Okay? Carbon and nitrogen. And then we're going to identify what kind of orbitals do those elements use. What kind of an orbital is carbon using? sp. It's using its hybrid orbital. And what kind of an orbital is nitrogen using? Here are the choices. One of the p orbitals, right? So now I've accounted for the other sp hybrid orbital on the carbon and one of the p orbitals on the nitrogen. You following? So now I have two p orbitals here and I have two p orbitals there. Those can't overlap end to end because they're parallel with each other. So they're going to do the pi bond and overlap side to side. So this one can overlap side to side, and the bottom is part of the same orbital. And so this electron is going to have to flip and be upside down. So those can coexist. So how do I describe that bond? It's not a sigma, it's a pi, right? Pi bond. It's between carbon and nitrogen. What orbital is carbon using? P orbital, right? I used up both of the sp orbitals. What I've got left are p orbitals. So carbon's using one of its p orbitals, and nitrogen is using a p orbital. So that's the description for that pi bond. As far as we are going in this class, pi bonds will always be between p orbitals, not hybrid orbitals. The hybrid orbitals are going to form the sigma bond, and the unhybridized p orbitals are going to be left to form the pi bonds. So carbon has, let's check off these. So we used up one of those p orbitals and another one of nitrogens, and now what we have left is a p orbital on the carbon and a p orbital on the nitrogen, and that's these guys that are sticking in and out. So this would be over the top of that, so you can't see that through there. And then back here, kind of get the idea. This is one of those things that if you just look at the drawing without having watched anybody draw it, it just looks like scribbles. Hopefully watching me draw it and explain it at the same time, you can kind of visualize. So these two orbitals are sticking in and out of the screen. And so this is overlapping in front of the screen, and this one is overlapping behind the screen. If the screen was there, you really couldn't see it. These are in the plane of the screen, and these are in the plane of the screen, but the one is in and out. So how would we describe this bond?
Pi bonds, P with
Yeah, pi, CP, NP. It's the same as this one. It's a pi bond, it's side-to-side overlap between carbon and nitrogen. Carbon's using a p orbital, nitrogen's using a p orbital. So there are three different kinds of bonds. There's the sigma bond between carbon and hydrogen. There's a sigma bond between carbon and nitrogen. And then we have two pi bonds. Because those are the same kind of bond, we don't necessarily have to write another description. Although if you wanted to, that'd be fine. So this is describing that bond and this bond. Actually, let's do it this way. Describing this bond and that bond. And this one is describing that bond in there. And this is describing this bond. Any questions? I'm drawing the pictures here because it helps us to see what's going on. I guess I should finish up what I was doing here. So I should finish up and cross those off. We can identify the bonding scheme and label these orbitals without drawing the messy picture. What we're doing is we're looking at these orbital diagrams and saying, okay, well, this one is going to overlap with that. This one's going to overlap with one of these. This will overlap with one of those, and this will overlap with one of those. When you have two p orbitals overlapping, it's going to be a pi bond. If you have a hybrid orbital overlapping with something else, it's going to be a sigma bond. The question is, why didn't I draw this arrow to the back as well? So this is one bond, this big messy thing here, and so I'm just pointing to one side of it, but it's only one bond. And this one down here and up here is one bond. So this oops, didn't mean to do that. That's one bond. There's a pair of electrons in it. It's weird because it's on both sides. It's like, how can it be there? Well, it's standing waves. The electron is a wave, not just a particle, and so that's how it can be on both sides at the same time. Any other questions? There are 3 different bond descriptions for this one. So what the worksheet is going to ask you to do, you've already done the Lewis structures on worksheet 9. That's why I asked you to take a picture of that before you turned it in. And so you can look at the Lewis structure. You're going to know how many electron groups, how many lone pairs, etc. And the worksheet then is going to ask you to draw the hybrid orbitals, the diagrams, and then the descriptions for how the bonds are formed. Okay? And we're working on it in class so that we can figure it out together. Okay, let's do carbon dioxide. So we do want to get through this chapter, so I'm not going to elaborate the Lewis structure for this. But we start with the Lewis structure. The Lewis structure for carbon dioxide looks like this. So how many electron groups? 2. So what's the hybridization? sp. So sp hybridization. So we can look at the carbon in the center and look at its atomic orbitals, s and p. It's got 4 valence electrons, so they'll be in here like this. And then we're going to draw the hybridized orbitals. From the 2 electron groups, we know we need sp. So we'll take 2 of those to be sp, and then we've got 2 orbitals left. And those are p. So the atom starts with 4 boxes, it ends with 4 boxes. You can't create orbitals, you can't get rid of orbitals. You have the same number of orbitals. So in the hotel analogy, we're moving walls and getting beds into different rooms, but the number of beds is the same. Okay? So how are we going to put the electrons into the hybrid orbital diagram? 1 in each. So 1 there, 1 here, and 1 there. I know to do that because I'm looking at the Lewis diagram and I'm seeing that there are 4 lines. That means 4 bonds. Carbon always makes 4 bonds in Chem 1A. It's awesome. I love always. Each of these is going to use 1 hybrid orbital for the first bond and then it's going to use p orbitals to make the pi bond for the second in the double bond. So this is what I need for carbon. So I'm not using this anymore. I needed to think about that though. So then let's look at oxygen. And the oxygen's not going to hybridize. So oxygen has its regular orbitals, S and P, and it has 6 valence electrons, right? So 1, 2, 3, 4, 5, 6. And conveniently, we see that there are 2 half-filled orbitals, and those are the ones that it's going to use to make the 2 bonds with carbon. This is why oxygen almost always makes 2 bonds. So let's predict the, lost the word, the bond description without drawing it first. So I have two of these oxygens, so it might be helpful to draw a second one. From my Lewis structure, I can tell that I'm going to need a bond between carbon and oxygen. The first bond is always a sigma bond. So I'm going to have a sigma bond. I didn't mean to do that. I'm going to have a sigma bond between carbon and oxygen. And we have to decide, okay, what orbitals is it using? Well, which of these SP or P will carbon use to make the first bond? It'll use the hybrid, right? So it'll use this SP, and then oxygen doesn't really have a choice. It's going to have to be a p orbital. So carbon's going to use SP, and the oxygen's going to use P. So we've used one of those and one of these. Carbon is going to make the same kind of bond with the other oxygen. So what we just described here is one of those bonds. I made that green. I don't know if you can tell that. We described this one. This bond with the other oxygen has the same description. So I was hoping you could see a different color. Let's try this. Well, it's pretty subtle. So the other sp orbital, hybrid orbital, will overlap with the other oxygen. And that's this one here. Okay? That makes sense? So what we've got left now, the carbon has 2 p orbitals, and each of the oxygens has a p orbital. So those are going to do the pi bonds. So we're going to have a pi bond between carbon and oxygen. What orbital is oxygen going to, I'm sorry, this is carbon. What is carbon going to use? P. And what's oxygen going to use? P. Those pi bonds are always with P. So one of these oxygens is going to make a pi bond with carbon. So that's this guy right here. And then the carbon has another p orbital, and this other oxygen has a p orbital. And so we're going to overlap those. And that's going to have the same description because it's the same kind of a bond. Oops, that's not what I meant to do. Does that make sense? Yeah.
Why does oxygen or carbon do this SP thing? I'm confused about that.
Because of what I said in the part of the lecture that you missed. Yeah.
And that's called hybridization.
Hybridization. So this is the sort of stuff you're going to do on the worksheet. Now I'm going to draw the picture too, just so that we can see what we were trying to visualize in our heads, or at least I was visualizing in my head. So the carbon has sp hybrid orbitals, one there and one here. Each of those is one orbital. And then it has two p orbitals, and the p orbitals are perpendicular to those hybrid orbitals. And so we have a p orbital up and down, that's one orbital. And then we have another one that's coming in and out. Okay, so there's my two hybrid orbitals and two p orbitals. So oxygen over here is only using p orbitals to bond. And so it's going to overlap one p orbital with the carbon, and that's the sigma bond here. So an end-to-end overlap, a p orbital on the oxygen, an sp hybridized orbital on the carbon. And then the oxygen also has another half-filled, oops, wrong color, another half-filled orbital. And this can overlap side to side with carbon's orbital, and that's the pi bond. Are you okay with that? And then we have an oxygen on the other side. The oxygen on the other side has a p orbital that can overlap end to end. Come on, move over screen. That it can overlap like that. And so that's going to form sigma bond. So this sigma bond, carbon sp hybrid orbital with oxygen's p orbital, this just describes this bond and the bond because they are the same sorts of bonds. And then the oxygen also has another half-filled p orbital. And so I'm going to draw this one in and out because of the carbon orbital that I have left. And so this is going to do side-to-side overlap. With the carbon. So we've got this in and out, and this in and out, and there's side to side. And now we want hamburgers. So let's put those two electrons in there. These pi bonds are at right angles to each other because this one orbital here can't make pi bonds with two oxygens. It can make one over here, and then it uses another orbital to do the side-to-side with the other oxygen. Now these oxygens also have an s orbital and an unhybridized p orbital that's full. So we could draw those in if we want to. So this one also has a lone pair here and a lone pair there. And the other oxygen, the same. Over here we've got an s orbital with a lone pair in it, and this one's going to have its lone pair sticking in and out. Any questions? Isn't this fun? Yeah.
So the pi bonds always touch in two places?
Yes. The pi bonds always touch in two places. They're always between p orbitals, not hybrid orbitals, but p orbitals. P orbitals have two equal-sized lobes, one on each side of the atom. And so what happens is each side bends and touches. And that's how you get this, you know, you've got above and below. One bond. Yeah.
Overall, if I'm looking at this, I'm looking at 2 sigma bonds and 2 pi bonds, basically?
Correct. There are 2 sigma bonds and 2 pi bonds.
Okay.
So this description applies to that bond right there and to this bond right here. Those are both sigma bonds. And our pi description applies to this bond and that bond. So our Lewis structure shows 4 bonds, and we've got 4 bonds in our picture here too. If it pleases you to write this again because there's 2 of them, I'm fine with that. Okay.